Yeah, okay. Okay, so just let me give you a brief introduction. So Dr. Shen received a bachelor's degree from the Tsinghua University, if I'm pronouncing correct, in China, and a PhD from the Yale University. He was an assistant professor and associate professor at Nanyang Technological University, Singapore from 2005 to 2015. He joined the University of Sydney in 2015. His research focuses on carbon materials and their sustainable energy and environmental application, including electrocatalysts, supercapacitors, membranes, antimicrobial coating. He is a fellow of the Institution of Chemical Engineers, the Royal Society of Chemists UK, and the Royal Australian Chemical Institute. He is currently serving as an editor of Carbon and Journal of Alloys and Compound. Welcome, Professor Shen. And the title of his talk is a thermo-osmosis coupled thermally regenerated thermochemical cycle for efficient lithium extraction. We all welcome you and thank you very much for giving time and coming for the presentation and giving presentation. Now the floor is yours.
Thank Professor Zadi for your kind introduction, and especially I want to thank Professor Sean Han, for his wonderful effort to make this workshop happen. As you may know, actually Sydney is already in lockdown for the last 3 months almost. It's a great opportunity for us actually to showcase our work, and also through this project, actually we get a chance to know people, also expand my own research. So today I will, because this is the first time I introduce our work to the group in Qatar. So I want to spend maybe about a half time to give a little bit of background of what I'm doing, different research area my group conducting. And then another half time will be talk about a specific research topic which we have carried out within this project, which is how we can better extract the lithium from the aqueous or liquid sources. So I'm actually a neighbor of Professor Shang. We are not at the same university. Our two universities basically are 500 meters away from each other. We are both in Sydney, and so it's the largest city in Australia, and the University of Sydney actually is the oldest university in Australia. My research expertise actually focusing on carbon materials. So carbon, I guess everyone knows if you come from chemistry background, it's a very interesting material. So you have 4 electrons, and then that's why you can form the different bonding among each other of the atoms. You could have sp2 bonding that will form a very nicely layered graphite structure, and you can also have sp2 bonding, which you have one atom linked to another 3. So then they will be able they will be able to have a very stable diamond structure. Now, especially I think the first speaker already mentioned that there's a number of the carbon material have attracted a lot of attention in the last 20-30 years. Start from the 1 zero-dimensional fluorine, and to a 1-dimensional carbon nanotube, to 2-dimensional graphene, and also recently they're more interesting on the carbon dots and the nano diamond. Now, even though they have been used in some application, but the usage of those carbon nanomaterial in different practical application is still relatively limited. If you compare to traditional carbon material, for example, for graphite, like all our lithium-ion battery basically using natural graphite. And then if you consider in, for example, for the active carbon, which have been widely used in wastewater treatment, so those use of the carbon nanomaterial still is relatively really limited. Now the reason, of course, in my view, there are two questions or two issues which have to be addressed to be able to really push those material into more application. For example, like already mentioned about the hydrophobic membrane. Then the two issues. First one is about the nanoscale structure control. So those carbon nanomaterial are different from traditional carbon is because the nanoscale structure are very different, are unique. However, for most of the synthesis method, it's not really easy to control the nanoscale structure. For example, for graphene, pristine graphene is highly hydrophobic. But once you oxidize it, it becomes hydrophilic. So how to precisely control their surface functional group to get the desirable property, which haven't been solved. So the precise or scalable nanoscale structure control is the first issue to be addressed. Then the second issue is they are small, they're nanomaterials. So normally it's a nanometer in size, maybe plane size are slightly larger, but still they're very thin layer. So once you put those nanoscale material together, their property basically totally change. For example, for graphene, suppose you have a high surface area, but if you stack multiple layer graphene together, the surface area become very, very small. Then for nanotube, you have individually, you have a high initial conductivity, but if you put it into bundle, so the contact resistance between each other, it's become very, very high. So to how to assemble them together into a macro scale architecture, which you may lose some property, but still remain some which are still useful. That's actually the second critical issue have to be addressed. So my research team basically are focusing on these two issues, and then we'll go into the different applications. So for first area which we have been working on many years is about the structure control of the single wall carbon nanotube. So nanotube you can consider as a hollow kind of the one-dimensional graphene you roll into a pipe, and depending on which direction you roll this graphene layer, so this is starting point, you can link this point to any other point on a graphene sheet, and then you will get the nanotube with a different diameter at the same time with a different rotation. So that rotation basically controls their electronic and photonics property. So you get about 1/3 of chance you will be produce some metal which is highly conductive, but then you have a 2/3 of chance you will create a semiconductor and with different band gap. So again, you can imagine if you want to apply it into application, if I want to have a conductive film, I actually need a high purity metal one. And then if I want to have a semiconductor used in electronics or in photovoltaics or for some biosensor application, I do need a semiconductor and the best with a precise rotation of the graphene layer control. Now, so that's actually quite difficult. So that's why we spend so many years to try to solve the problem. The way is we control the catalyst and the metal clusters, and eventually using the metal cluster to control the growth nanotubes. We actually now can produce some specific type of nanotube. They are semiconducting with very high purity, and so those can be applied into different electronic device applications. Then another area is for energy storage area. We know that actually graphite is used in the lithium-ion battery, so there are not of energy storage device or different applications. But most of the case, you put the material in a rigid casing and they're not flexible. While a trend in terms of the device development is for become flexible and become wearable. So our cell phone, and now you can already see Samsung already sell the foldable phone. So in 10 years down the road, the not all electronic device will become flexible. Now, in order to meet the requirement, then of course the energy storage and all the other component parts have to become mechanical flexible at the same time. They will still be able to store the energy. So the carbon nanomaterial, because they're mechanically flexible and all those advantages in terms of their high surface area and a high electrical conductivity. So people are considering to apply them into different wearable device application. So our team are mostly focusing on this 1D fiber based device. So that involved how we assemble those nanomaterial and nanotube and graphene together into one-dimensional fibers, and those fibers then will be able to use for building small devices for energy storage. And there are also issues about how to incorporate other material into the carbon composite, because the carbon material itself sometimes they have relatively low energy storage capability, so we need to add in other material in. And adding material in is not trivial, because if you add it too much, they will block the pore, and if you too little, then they don't have much effect. So we're actually developing different approach to incorporate them together. And also because it's a one-dimensional fiber, So you can imagine the device is different, just like a clothing. So if we build the energy storage device into fiber, then that can be waved into textile structure. For example, the band, the waistband here, or different kind of textile structure, and then that will be able to move into your clothes, the energy storage device. So that's for the energy storage. Another area which we are working on is using carbon material as a catalyst or as a substrate for the catalyst. Now, the idea or the driven is, I think Qatar is produce a lot of the natural gas and a lot of the oil. Now, but people have concern that we should use more renewable energy. Now, in order to use this renewable energy, let's say, for example, electricity generated from solar cell or wind or hydro, then they have to be converted into something which can be easily transported. So using the electricity to split the water to produce hydrogen, or to convert the CO2 into, let's say, the CO or the methane or methanol. So those activities need a catalyst. While carbon material, especially carbon nanomaterial, is a very good potential candidate for those catalysts. On the one side, they have a large surface area, high conductivity. On the other side, if you doping different elements into the carbon, they actually become catalytic active, so they can serve as a catalyst. So we started this part of the work from 2013. Initially, we are looking at how to dope the graphene, dope the carbon nanotube with the different components. And then we noticed that actually we can also use the bio precursors, for example, the bacterial cell or the milk powder, and those can use as a precursor to produce a very high activity catalyst. More recently, we are looking at the more molecular level. So how can we precisely control the atomic structure of the different components in carbon, as well as how can we anchor a molecular catalyst on the carbon surface, so we can precisely determine their activity and as well as their stability, so they will be able to serve as a better catalyst for those reactions. So for the membrane area, because I'm actually not a membrane expert, we are carbon material, so the main effort we have is to working with the membrane researchers to incorporate the different carbon material into the membrane, because the carbon material do provide the opportunity to tune the carbon, to tune the membrane properties. For example, for the graphene, recently we have done the work to using graphene film, compressed graphene film for the organic solvent separation. That do show some advantage because the carbon are much more stable in the organic solvent. Then the last bit of the area is more kind of in a way is for fun, because as a carbon researcher, we do interesting on how carbon interact with different biological system. So we try to understand when they put together with the bacteria, how they interact with the bacteria. So we reported some of the earliest work on how the carbon nanotube and the graphene will be able to kill the bacterial cell. It's a very complicated problem. It's involved with how is the property of the carbon, as well as how is the environmental condition, like what's the solvent environment, what's the additional salt in a solution, as well as what kind of cell you have. So that will influence how the carbon material interact with the bacterial cell. Eventually, in some situation, we will be able to kill the bacterial cell very efficiently, while in other situation, they actually will be very safe and stable. So those understanding, there are multiple implications. One, of course, is if we put those carbon nanomaterial into application, eventually they will go into the environment. So we need to understand the environmental impact. Second is we do come using some of the carbon material to build the necessary water filters that will be able to kill the bacteria when you filter the water through the carbon-based membrane structures or the forms. So that's about some of the fundamental research. We also have an industrial part of the work, which is actually that maybe could be relevant to Qatar. So Australia have a lot of the methane. Methane is still considered a greenhouse gas because you burn the methane, you still produce CO2. There's one particular part is you can directly split the methane into hydrogen and solid carbon using, let's say, the catalyst. Now, we're working with this Australian company. They're using iron ore, basically a very low cost material as a catalyst, so that's remove the problem of regenerate the catalyst. Then we can directly split the methane into pure hydrogen and carbon. So our work is mostly focusing on the carbon part, because you can see here, if we split methane, 1 gram of hydrogen will produce 3 grams of the carbon. So the huge amount of carbon will be solid carbon will be produced. So we are looking at how to utilize this carbon for different applications. I guess that's about half the time. Want to introduce the general different area topic we are working on. Now, in the next half time, I will focusing on one particular specific project is within the collaboration with Professor Shang. So that is how we can extract lithium more efficiently from the aqueous sources. Now, we are focusing on this particular type of the configuration, which is the selective ion exchange. I believe, I think some of the students may be working on this area, so you may be familiar. So what we are doing here is we have two electrode. So one is based on the lithium manganese oxide. That's basically integration type of the electrode material. The lithium will be able to go in. And another side, then we use a Persian blue argon. So that's the nickel hexane cyanoferrate. So it's nickel HCF. So that actually can be able to capture and release the potassium. So by during the discharging, we insert the lithium into the MO and release the potassium into the solution to have a charge balance. While during the charging, and then we do the reverse steps. Now the problem of this one, the advantage first is of course is highly selective, then also much more faster than other lithium the extraction method from brine. But the problem is they are not very efficient if your concentration of the lithium source is very low. Some situation, for example, if you want to extract lithium from seawater, basically the process is so slow they not be able to go into the electrode. Then the second one is you do need a lot of electricity, especially during the discharging process, to drive the lithium out. So this is the major electricity consumption. So our initial thinking is how can we do something to reduce the electricity consumption as well as to improve the performance in no lithium concentration sources. Now, when we look at the energy consumption part, one of course is reduce energy consumption. Another one is can we generate electricity from this process. Now, there's one particular process which has been studied by many people. That is called the semi-regenerative electrical chemical cycle. What happens if you have two electrode pair? The electrode potential basically will change based on the temperature they are in. Now, that depends on the electrode material property. So some electrode property material, they have this positive temperature coefficient. So you increase the temperature, the potential will increase, and some have a negative. Now, if you put the two electrodes in a pair, then you have the whole cell thermal coefficient. This alpha here becomes the difference of each other. Now, the thing is that if we have a cell built with two electrodes, and if they have a temperature coefficient which is larger than 0, then we can actually do the discharging of the cell at a relatively high temperature here. And this is the amount of the energy that will be released. And then we can charge the cell by lower the temperature of the electrolyte. And here is the charging. And this is the energy you needed to charge the cell. So the difference between the discharge and the charging, and this green shaded area, is actually the electricity that can be generated from the whole circle. Now, they are not generated by itself. It basically comes from the hot heated the electrolyte, which is the thermal energy. Now, this temperature no need to be very high, as long as, let's say, for example, 60 or 80 degrees. So on the Earth, we have many abundant low temperature thermal sources. So those energy normally is wasted. So if we can use this kind of cell to harvesting the thermal energy, then that will be able to generate electricity. Now, on the opposite side, of course, is if you have a negative thermal coefficient, then you do the discharging at the low temperature and do the charging at the high temperature, and then they can also generate electricity. So then the question is, can we using the neutral pair, which is MO and the nickel HCF, which people have been using for the lithium extraction to harvesting energy, and then particularly in our electrolyte or in our aqueous environment, which is similar to the brine or the salt water, which people used as the liquid source to extract the lithium. So we done the test, and then here you can see that. So for the nickel HCF, you actually get a negative energy coefficient, the temperature coefficient. And for the MO, it's actually roughly positive, but it's quite close to zero. But the good thing is when you pair them together, they actually get a very positive temperature coefficient, which means we can use this pair of electrode and in electrolyte, which is similar to the source solution people are using to extract energy. So that's the step one. Then the step two is since we already have the heated, we may use the heated source solution. Then we can also integrate that one into a membrane desalination process. I think most of the membrane experts know about this one in detail. So if you put this hot solution here, then the water moisture will go through, condense to another side. So which means if we couple this thermal osmosis process with a lithium extraction process, if we use a heated source solution, we will be able to generate fresh water. At the same time, we can also continuously concentrate the source solution during the whole extraction process. So that's going to...
You have 5 minutes to finish, please. Okay.
Sure, I will try to finish it. Well, not much of a page left.
Thank you.
So that's where we will propose this idea. So we couple thermal osmosis, which you can use to generate fresh water as well as concentrate the soil solution with generative cycle here. Then they will be able to basically do the discharging or the lithium extraction at a relatively higher temperature, 60 degrees. The same time that you do the discharging at 20 degrees. So ideally is we do the charging at the low temperature and do the if both are the low temperature, then this is the energy consumption you will be used. But if we push the charging temperature, discharging temperature higher, and here's the energy saving we could have. So this is theoretically, I believe, it will work. So that's why we move on to build our cell to test this idea. So here's the cell setup. You have the membrane module, and on this side we have the IMO on the one side, and have the nickel HCF on the other side. And here the chamber for the extraction, and then we put the membrane. Unfortunately, we still use the PDF of the standard polymer membrane because we are not expert on the membrane. So we just buy the commercial one to use. And on this side will be connected for the fresh water. And here's a different tank, and this is what it looks like in the lab. This is a very small cell. So this is a diameter about 3 or 4 centimeters in diameter. Now, then we move on to test the performance. So here you can see, first we want to verify, can we really extract electrical energy from the system? Because theoretically work, and in practical they may not work. So here we try 3 cycles here. And this is a cell, then you put into a 60 degree solution. When it's stable, then we do the discharging 20 minutes. Afterwards, then we take it out and put it into a low temperature 20 degree solution to recover the lithium. And then that's a discharging process that go on 20 minutes. And so this is repeated for 3 cycles. And this is basically the voltage change on the low temperature and high temperature condition. And here you can see this is the energy input we need to put in to charge the cell, and this is the energy output we take out from the discharging process, and here the energy consumption. So compare with the cell, if we don't change the temperature from 20 to 60 during the discharging, we can save about 20%. There's a lot of energy lost from the reactor because we are not fully insulated, but even use this very small scale lab cell, we can simply just very easily to just save 20% of electrical energy used to extract lithium. And then for the performance of the lithium extraction, they are basically very similar to the low temperature process. And we can see that we have a repeat for 20 cycles. The lithium extraction purity remain as more than 23%. then you can continuously extract lithium. So for this membrane, for this small membrane cell we built, you can actually accumulate more than 1,000 millimole per square centimeter of the membrane surface. And then also the selective ratio between lithium sodium, lithium magnesium, and lithium potassium, they remain reasonably high, so they don't actually have a significant performance decrease over those 20 cycles. Then the last part is the fresh water generation. And as you can see that we can generate actually quite a fresh, just a fresh water from the membrane desalination with very high salt rejection rate. And then you can continuously produce a fresh water, even though it's not too much, but still the fresh water can be generated from this lithium extraction process. So this work has been published. So we move on to this step, because what we observe is the cell work quite well if we're using brine, which is a high concentration salt, relatively high concentration salt, but with a sodium lithium ratio of about 100. But if we want to try to use the seawater, so they have a much higher, it's normally about 20,000 ratio between sodium and lithium, the performance go down dramatically. This is for standard cell. But we found that this actually is depending on the temperature, also depending on the concentration. And using this new system, we have proposed, and the result basically will show that we actually be able to extract lithium from simulated seawater with very, very low concentration. So this work still in the process of the for the submission and publication. So hopefully will come out very soon. So in summary, we show that for using this new process, which integrate the thermal osmosis and the thermoelectrical cycle, we will be able to extract the lithium similar to the regular lithium electrical extraction process. The temperature no need to be high, 60 degrees, so that heating of the salt solution could come from various low temperature salt waste heat. And then the lab test show that we can save at least 20% of electricity through better insulation. I believe that could even be better. Then at the same time, they do produce fresh water from the membrane desalination part. So I think that's my time is up. So that's my group and the funding agency and so on. Thank you everyone for listening.
Yeah. Thank you very much, Professor Shen, for very interesting and nice presentation, especially the overview of the nanomaterials for this energy and environment application, as well as for electrochemical process for lithium recovery. Now we will, sorry, I need to skip questions at this point. If somebody have questions, then we can certainly discuss with him. We need to catch the time. So again, thank you very much, Professor Shen.
Sure.
We will move to the next. Thank you very much for your interesting talk and for giving time for this presentation and giving opportunity to hear to you. Thank you again very much.
Thank you.
Yeah. Now we'll move to the next presentation by Professor Ephraim Curcio from the University of Columbia, entitled Membranes at Water Energy Raw Materials Nexus. And Professor Ephraim is a full professor at the Department of Environmental Engineering, University of Columbia, and CEO of Saligenda Membrane Technology.